Here's a fairly standard frameworks question where we're going to be looking for some tensions and thrusts within the rods in the framework, and it will involve using moments and resolving forces in equilibrium. In the first part of the question, we need to show that R equals 150. So R is this reaction force at A. Now, we've got a couple of 120 Newton forces, and we don't have any information about what's going on at C. So there may well be a reaction force at C, which, if we take moments about C, the perpendicular distance of the direction of that force from C will be 0, so we won't need to worry about that force. So we'll start by looking at moments about C. Now this shape is in equilibrium, so all of the moments which would cause the shape to try to turn in a clockwise motion about C will be balanced by the moments that would try to turn the shape in an anti-clockwise motion about C. So we've got the force of R newtons, which if we were to push that, then it would rotate about C clockwise. The other two forces would cause it to go anti-clockwise. So we've got 4R, so 4 is the distance from C, that's the perpendicular distance of the line of action of the force, and these are 2 metres long, so we've got 2 there plus 2 there, so that's 4 times R, and that's balanced by the other two forces, so we've got 120 times the distance of 2, and then we've got 120 here, and then the perpendicular distance from that force to C is 3 units. So we've got that 4R is 120 times 2 plus 120 times 3. So if we rearrange that, we get R is 120 times 5 divided by 4, that's 600 over 4, so that's 150 newtons. Now this was a show that question, so I have just made sure that I've set my working out nice and clearly, because they've given me the answer of 150, I need to show how that's been gained. In part 2, first of all I need to draw a diagram showing all the forces acting at the points A, B, D and E. So A, B, D and E were 4 of the points given on the diagram. I don't actually need to show the values of the forces around point C, although I will include C on the diagram. And it says to include the forces internal to the rods. So we've got the external forces, we've got the R which is 150 newtons, and the force E of 120 newtons, and a force at B of 120 newtons. And then all the internal forces are all these values that may be tensions or thrusts, which is another word for compression. And we can label them in any way. Some people like to call it T1, T2, T3 and so on. I like to keep track of where each force is, so the force that's in the rod AE, I'll call that tension T with a subscript AE, and then the force in the rod AB will be T with a subscript AB, and so on. So I'm going to look for the internal forces in rods AE and AB and determine whether each is a tension or a thrust. I can leave my answers in surd form. Now, if it didn't say that, I would have used surds within all my calculations, but I might have rounded final answers to 3 significant figures. But I wouldn't use the rounded values to calculate other values. I'd always go back to the exact values in surd form to do all my calculations with. So I've got my diagram from before, and the first force I'm looking for is in this rod AE. Now if I look at A and think about resolving forces, well, horizontally I've got this tension in AB which I don't really care about, they haven't asked me about that one. And then I've got this tension here of AE, which I do want to find, but that's not going to be the easiest way to approach this. If I look vertically, then there's no component of this tension in AB acting vertically, so I can effectively ignore that one. So vertically, I've got the 150 newtons and I've got a component of tension in AE. So I'm going to use that and resolve vertically using the fact that it's in equilibrium. Now I could do that as the sum of all the forces equals 0. I like to think of it as just forces up equals forces down. So with the way I've drawn my diagram, if this tension actually is in that direction, pointing from A to E, then that would be tension. If it's actually in compression or thrust, the diagram would actually be that the arrow should be the other way, and that will be indicated by a negative answer. So I'm going to go ahead with it in the way that I've drawn it here. So I'm resolving vertically at A, and I've got my 150 newtons upwards, and I've got the component of this force, so that's tension in AE sine 60 is the vertical component, and then going downwards I've got 0 because there are no arrows pointing downwards on my diagram. Now sine of 60 is root 3 over 2, I'll use that exact value, and so I'm just going to rearrange this. I'll subtract the 150 from both sides and then divide by sine 60. So dividing by root 3 over 2 is like multiplying by 2 over root 3. So my tension in AE is minus 150 multiplied by 2 over root 3. So that's minus 300 over root 3, so that's minus 100 root 3. Now that negative sign tells me that this rod is actually in thrust. So I'll give my final answer that the rod AE is in a thrust of 100 root 3 newtons. To find the force in the rod EB, I'm going to do the same sort of procedure, this time focusing in on E. And again, because I don't care about ED, I'm going to look at resolving vertically and the fact that it's in equilibrium. So if I'm resolving vertically at E, I've got the 120, which is going downwards, and then also going downwards, so I'm adding. I've got TAE, this is the value I found before, and the vertical component is going to be TAE cos 30. And then I've also got the one I'm looking for, TEB, and that's cos 30. And that's equal to 0 because there's no force going vertically upwards. So I'm going to use the fact that cos 30 is root 3 over 2, it's actually the same as sine 60, and rearrange this equation. So I'll subtract 120, I'll subtract TAE, which is minus 100 root 3 cos 30, and then divide by the cos 30 to get TEB on its own. So if I evaluate that, I end up with 20 root 3. Now that's positive 20 root 3, so I know that this one is in tension. So I'll write out that my final answer is rod EB is in tension 20 root 3 newtons. Now this one's a little bit strange. It's asking me to explain without any further calculation how I can tell that rod ED is in thrust. So rod ED is this one across the top. Now I've already worked out AE, that was in thrust of 100 root 3 newtons. So the fact that it's in thrust means rather than this arrow pointing in the direction I've got it, I could actually draw it in the opposite direction. So its horizontal component is acting to the right in the direction of ED. Similarly, EB is in tension, so its horizontal component is acting in the way that I've drawn it, so that one's to the right. So if those two arrows are both actually acting towards the right in the direction of ED, then the force that's internal within ED acting at E must actually be acting to the left, so in the direction from D to E. So that means that that one is in compression. Now, if they hadn't said without any further calculation, I'd probably just resolve the forces horizontally at E. It would be very easy to find the value of the compression in ED. But they said without further calculations. So I'd go for something like saying that the horizontal components of the forces in AE and EB both act in the direction from E to D, so the internal force in ED must act in the opposite direction at E to have equilibrium, so that means ED is in thrust. Now this is just a 1 mark question, so hopefully that will be clear enough to gain that mark. In fact, if we look at the mark scheme, we can see the first part of the question, taking moments about C and showing sufficient working, that was just 2 marks for doing that. Then the diagram, here's the diagram. Now they haven't actually included the point C on their diagram. I think it was okay to include it. I didn't include any forces at C, I just had it as a point to be clear where I was. And they've used the same sort of labelling structure that I used. And then they resolved vertically at A and at E, and came up with the same values. They've used C for compression and T for tension. And so plenty of method marks here. And final answer, they've said to consider horizontally at E, using the results from part 2, gives ED as thrust. Now that in itself is not very clearly explained, but it does actually say they'll give you the marks if you have clearly explained it. Even if you've used the wrong answers to the previous part, you'd be able to pick up that mark if you've understood what's going on there.